Evaluation of definite integral. We know there are two methods to evaluate a definite integral. First, using the fundamental theorem of integral calculus, and second, the integral as the limit of a sum, definite integral as the limit of a sum. We have seen how we can find the integral using fundamental theorem of integral calculus that we have seen earlier. Now here we discuss the evaluation as a limit of a sum. For this, consider a function fx which is continuous on the closed interval AB. Closed interval AB. And then this integral a to b fx dx is equal to the area bounded by the curve, the x-axis, and the ordinates at x equal to a and x equal to b that we know. Area is this. And now our aim is to derive a method which will give us the area, this area. And now consider the graph of the function. Suppose this is the graph of the function fx, and suppose this is a, and suppose this is b. Then integral a to b fx dx is this area under the curve, the x-axis, and in between these ordinates at x equal to a and x equal to b. And to derive this result, the area, we divide first this interval from a to b into a number of subintervals. So suppose this a, this point a is a some x naught, and another x1, x2, x3, x4, etc., xr or xr minus 1, xr, etc., this xn which is equal to b. Divide this into a number of subintervals. And consider a subinterval xr minus 1 xr. Suppose we draw the ordinates at these 2 points. So here we have an area corresponding to this subinterval. And suppose the width of this subinterval is h. And now we have divided this interval AB. So the distance AB is b minus a. And divided this subinterval into n equal intervals of width h. And therefore we see that this h is equal to b minus a by n. This width is this b minus a divided by n. B minus a divided by n. And now the area, suppose this is the point say P, this is the point Q, and R, S. Integral a to b fx dx is the area of this region P, Q, R, S. And now suppose this XR, this point is capital A, this point is capital B, and this point is capital C, and this point is capital D. And suppose we draw the perpendicular from D to this BC. Suppose this is L. And again suppose we extend this AD and join or draw perpendicular from C to this. So suppose this is L, M. So in this we have three regions, areas. One is this ABLD, which is a rectangle. ABLD, which is a rectangle. And the other is ABCD, which is the area under this curve, the x-axis and ordinates at A and B, this region. And another is ABCM, this ABCM, which is again a rectangle. This ABCM, which is again a rectangle. So these three areas, consider this. And then here we see that this area ABLD, which is less than area ABCD, which is again less than area of ABCM. ABCM. From the diagram it is clear. And now, suppose we make this width AB, that is this H, very small, very small. Very small. And then we see that this H or B minus A by N tends to 0, nearly equal to 0, tending to 0, very small. Consequently, we see that the number of the subintervals will be increasing and that the n number of subintervals will tend to infinity. The width becoming very small, nearly equal to 0 means the number of subintervals will be increasing and tending to this infinity. So this h tends to 0 is equivalent to n tends to infinity. N tends to infinity. And in that situation we see that these three areas will be almost equal or equal. Very negligible difference between these three areas. And now, suppose we add these areas of such subintervals, all such subintervals. In that situation, this will become the area of the region bounded by the x-axis, the curve and the ordinates set x equal to this small a and x equal to this small b. That is, this integral need to be fx dx. That will be equal to the sum of such intervals or sum of such intervals. And now we can write these in step-by-step form. Suppose SCN, small SCN, be the sum of these small such intervals, sum of all these intervals. Then the first area, first region will be this height into this width. Here this area of this portion will be this height AD into this width H, AD into H. Similarly here we see that this PS into H. But what is this PS? PS is the ordinate at x equal to this A. X equal to this A is H naught, of course. So That ordinate is what? This function is fx, and we draw the graph as y equal to fx. So ordinate means y. So the value of fx, small fx, at this x naught is this height. So the area of first such region is this h into fx naught. The next will be h into fx1 plus etc. and last h into fxn minus 1, this. So this plus h into fxn minus 1. So this is equal to this h into sigma fxr r from 0 to n minus 1. This is small Sen. And again this capital Sen areas of such rectangular regions, all sum. So here the area of this will be h into this height, fxr. So area of first such rectangle will be h into fx1. First will be fx1. So which is equal to this h into fx1 plus h into fx2 next plus etc. plus h into fxn, which is equal to h into sigma fxr r from 1 to n 2. And this area that will be this integral a to b fx dx. And here we assume this interval is very, very small, h is very, very small, tending to 0. So that factor should be indicated in this expression if this one to be coinciding with this or this. Therefore, that can be indicated in this form. Limit n tends to infinity, Sen is equal to limit n tends to infinity, capital Sen is equal to integral a to b fx dx. And we can take any one of these two to evaluate. Usually we take this to evaluate. Therefore, this integral a to b fx dx, this integral a to b fx dx is equal to limit n tends to infinity, or equivalently this h tends to 0. N tends to infinity, h into sigma r from 0 to n minus 1 fxr, which is again equal to, here h is equal to this b minus a. So this is equal to limit n tends to infinity, b minus a by n into sigma r equal to 0 to n minus 1 fxr. So this is the required area as a limit of a sum. This is a sum of these fxr's. The limit as h tends to 0 or n tends to infinity. So this is the required area or the required definite integral value of the definite integral. Okay, that's all.